Um, so, yes, as Pierre-François just says, this is my last lecture. I'm astonished at how quickly the week has gone, and I'm already feeling sentimental looking at having to leave this beautiful place and this wonderful company that you all have provided. So I hope that you all are finding this worthwhile and are prepared for 3 more weeks of fabulous learning, which I think you will get. Um, Now, after paying everyone a compliment, I want to tease everyone. I prompted you all last week to be prepared to challenge Stefan when he came here with the question of how much is understood about how often we get to the modeled low frequency noise and how hard it is to often achieve that. So please hold his feet to the fire, or maybe you should hold their feet to the fire as designers, how to make sure that if the taxpayers of Europe or the United States or the world are going to spend $1 billion on one of these low frequency things, that it's going to work at low frequencies. So please do this with both boldness but also humility. Um, I will, in the course of my prepared material today, say something else about boldness and maybe lack of humility. So to motivate what I'd like to do to finish up my presentations for the school, I went back to a slide I used a few days ago where I tried to make the point that gravitational wave detection is so hard to be considered nearly impossible. And if we look back at that, you can see that we've talked together about building the raw sensitivity, how an interferometer can be shot noise limited and how the shot noise can be made low enough to achieve this otherwise astounding precision. I had one mealtime conversation over this. Didn't make much prepared material. If you're still wondering about that, we can talk more about it over lunch or dinner. How we can do this with things made out of atoms. We also talked about how to tame the much larger mechanical noise sources, at least several of them, featuring seismic noise and thermal noise in particular. But today I'd like to talk about a subject that is mainly about achieving this last challenge on my list of nearly impossible challenges, namely how to do all of this given that in order to have a quiet, well-isolated interferometer and one whose response to gravitational waves we can understand. For all those reasons, we need to use free masses, but nevertheless, we need the interferometer to work as reliably as Michelson's original interferometer, where he and the people who helped him built incredibly stiff, beautiful, uh, uh, rigid mounts to hold all the optics. So that's actually a really interesting challenge. And it's also a challenge that involves, I think, some of the most beautiful technology in our field. This is the field of technology called control systems. And by the end, I hope to convince you all that this is both magic and beautiful. Magic in the sense that it seems like it shouldn't work, beautiful in that it's incredibly powerful, and it's incredibly powerful in a way that we as physicists can understand. And I'm making the we as physicists point because it's a matter of great pain to me that physicists aren't generally in our standard education taught anything about this. It's relegated to departments of engineering, at least in the United States. You all from other educational systems can tell me if it's any different anywhere else, but it's too beautiful to be left to engineers. Physicists should claim this material, so I'm on a campaign for that. So after I talk something about control systems in the abstract, I'll walk us through a few examples that play roles in various subparts of gravitational wave interferometers. The simplest one to look at is active damping, damping with a control system rather than with material friction, and Maybe we'll work through a bit of how active vibration isolation works. But then I want to talk a bit, not so much from the point of view of formal control design, but from the point of view of war stories, about locking some of the really twitchy aspects of gravitational wave interferometers. One of them is just an individual Fabry-Perot cavity itself. The other is a whole interferometer made up of multiple coupled Fabry-Perot cavities. And by the time that's done, I think you'll have a sense of how we've come up with a rigidifying function without actual rigidity. I'll want to make sure that you understand the price that's paid for this magic, because unfortunately it isn't actually magic. We'll see what the challenges are, and then I'll try to wrap up a bit. So first, let me just show you a few pictures of things that we know already based on things we've talked about before that we need to control. And one of them is the length of a resonant cavity. And you can think of this, if you want, as the world's worst scale drawing, with this representing a 4-kilometer long arm cavity. And here is an end test mass with its highly reflecting mirror. And here's an input test mass with its partially transmitting mirror, so light can couple in through the substrate. And I won't, at this moment, tell you exactly what all these components are, other than to say this is a schematic representation of how you can set up a system that can, do two functions. One is to sense whether the cavity is on resonance or not, and the second, which is not so well diagrammed here, but somehow find a way to then act on the cavity so that if it's not in resonance, to drive it towards the resonant state that we want to keep it on. So this is a system we'll want to control, and I'll talk something about it. Here is a very simple looking diagram, a sketch of a test mass suspended as a pendulum, and every interferometer design that I know has its at least one pendulum stage, because this is the best way to get low thermal noise, seismic isolation. But remember, if we want low seismic noise, we want very high Q. And when I showed you the benefits of high Q in a diagram, a graph of a thermal noise power spectrum, obviously, yeah, we want that high Q. We want to put all that half kT's worth of energy in the resonance and make those wings very low. I don't think I sufficiently reminded you all that, but I think we did talk about that in response to a question, that a high Q pendulum means it gets disturbed for any reason and it oscillates for a really long time. And the notion that we can let that ring down once and never disturb the test mass suspensions again, I've never seen an interferometer go without disturbances for more than a day or a couple days, and some days are much worse than that. So the idea that maybe we want to somehow, in some delicate way, modify the behavior of a test mass suspension while not ruining the noise properties that led us to that design in the first place is something that we'll talk about. And as yet another example, I'll ask us to think about, at least in principle, and we'll see how time is ticking away, how much work we want to do on it in detail, but let's think about whether we can supplement the vibration isolation that you get from connecting masses through springs and maybe cascading several such stages. That's our prototype of vibration isolation, but maybe there's a way to use control systems to modify the properties that actually improve the vibration isolation beyond what it's easy to engineer with strictly passive mechanical techniques. I'll at least suggest that, and maybe more. And finally, we will spend some time on talking about how we get the equivalent of this stone table and these beautifully rigid mirror mounts of this advanced Michelson interferometer from 1887 without the rigidity and without the mounts, and where adjustments can be made automatically and remotely and not by some assistant having to go over and turn a screw. Okay. So those are the challenges to which we want to apply this technology that's almost as cool as magic. And here is a diagram where I want to introduce the key concepts of what a control system is based on feedback. And I'll sometimes call this thing a control system, sometimes I'll call it a feedback system for reasons that will become obvious in a moment, and sometimes I would call it a servo. That is slang. Servo mechanism is the longer term that some journal editors will insist you write in a paper. The word servo itself is grabbed from Latin, I believe, servus meaning slave. So this is a kind of a automatic slave that you don't have to pay to do work that you would otherwise need doing. So we're going to stare a lot at this diagram, so let's get familiar with the different generic parts. And the terminology is pretty standard in the servo engineering literature, so it's worth learning. All right, so this is, first of all, I should step back and say, what are these rectangles and lines? This is a so-called block diagram, and in this block diagram, I'm going to represent a system. In this case, I mean something that has an input and an output and a well-defined linear relationship between input and output. And I'm going to think of a generic system as consisting generally of 4 different linear systems. We'll name them in a moment. So rectangles represent linear systems playing various roles, and along these various lines that connect the rectangles are signals, either input signals or output signals. And some of them are important enough for us to name because we imagine looking at them. There are also inputs. In general, there can be a control input and a disturbance input. And it's really important that we have some junctions, some summing junctions. So here is a place where the servo's internal input is summed with a control input that you might want to apply. Here is a place where the feeding back of this system called the actuator on the plant is summed with inputs that you didn't want but that are an important part of the environment, so-called disturbance inputs. So that's how to read individual black marks on the screen. Now let's see what the diagram actually represents. So the first and in some sense the most important system we want to think about is the one with the strangest name. It's always called the plant. And first I'll tell you what it is, and then I think I can suggest why it's called the plant. The plant in servo technology is the pre-existing system that you want to control or modify the behavior of. So if you are a controls engineer, the plant is the thing you didn't design, that your supervisor, your employer, whatever, says, here, fix this, it doesn't work. Use the magic of controls. I think it's called the plant because this goes back to the application of feedback control to chemical process systems. And so this literally represents a factory, okay? And at least in American English, factories are often called plants. I think that's where the term comes from. All right, so this is the thing that you imagine is pre-existing and that everything else is skill/magic that you're going to apply to it. So what are the other 3 generic parts of a feedback control system? Well, you always need some kind of sensor to figure out what is the output of the plant, because at the end of the day, your goal is to have a better kind of output than you would have had in the absence of feedback. So you want to know what that output is, and it's the sensor's job to measure that. So often it's the case that the sensor's output itself is the thing that you pay the most attention to, but sometimes there are various situations where other parts of the world that you're trying to make better see the plant output directly. And I'm distinguishing between this because most of these things have interesting dimensions. All right, the plant, let's imagine that the plant is the mechanical parts of a gravitational wave interferometer, and its output might be the differential arm length between the arms measured in meters. Well, sensor, we want to somehow measure that and have something, for example, in volts or digital counts or something like that. So the sensor, in addition to doing some physics magic in the world of this diagram, is also changing dimensions of things. We'll talk more about dimensions in a moment. So you're almost always, I don't know of a situation where you don't need a sensor. And I also don't know of a situation where you don't need an actuator. And the actuator is the linear system whose job it is to somehow know what kind of corrective influence to apply to the plant in order to make the behavior of the plant better, and at the end of the day to make the output of the plant be more like you wanted than it was doing in the absence of feedback. So here's the thing you're going to fix. Here's how you can see what it is doing. Here's how you can apply an influence in order to fix what it's doing and make it better. And then there's a fourth kind of system that goes into a complete feedback control system whose function is not yet obvious. And I'm going to hold off on explaining exactly what the role is of this fourth system, the one drawn at the bottom called the filter. For the moment, I would like it to suffice to say that I've never seen a control system that didn't have some interesting choice made in the filter as well. And in fact, this is the one where you, as the control engineer, if you have put yourself mentally into the position I'm inviting you to do, this is where you do your design work to make sure that, given your plant's behavior and given its and your goals for it, and given your ability to measure it and to push on it, here's where you apply your thinking in ways that I will explain in a moment to make sure that this whole closed loop system behaves in a better way than the system consisting of the plant alone. So let me mention some more jargon. Sometimes we say we want to have a jargon term for no feedback applied. The jargon term for that is open loop, to contrast with what you do when you're using feedback or controls to fix something, namely closed loop behavior, because look, you can trace a signal all the way around a closed loop. So I will often switch into this jargon. If you forget what it means, raise your hand and I will remind you. Okay? Open loop uncontrolled, closed loop controlled. Okay. Any questions about what the diagram represents before I go on to turning it into specific examples? Okay. Let's talk about some goals. All right. This is actually a really important goal for us, even though it seems like the most boring thing in the world. One of the most important uses of feedback or of control is simply to hold a plant near a chosen operating point. Sit still, please, okay? Sounds boring, but we can already see, I think, why it's so crucial, because we are looking for these influences that are as close to zero as anything measured in the in an environment that would tend to make the interferometer move a lot. And part of the reason that that's so horrible to contemplate is we are making our measurements of differential arm length or gravity wave strain with a readout system, those resonant Fabry-Perot cavities, that only give a linear phase response to a length change in a very tiny region. So unless the interferometer is sitting very close to the operating point, not only would you say, oh, there's a lot of noise, the signal is absolutely meaningless. Okay. I'll remind you of that again when I show you the characteristic response of a cavity readout system. But it is crucial to reduce the sensitivity of the plant that is a free mass interferometer, reduce its sensitivity to disturbance inputs. Otherwise, we can't make any sense of the output. Another kind of goal for feedback is to simply modify the dynamics of a plant, to take something that's a high Q oscillator and make it behave as if it's lower Q without wrecking the noise advantage of the high Q mechanical system in the first place. Rather than reading all these words, let me, in a moment, I will show you an example where it's obvious that our goal was to modify the dynamics of the plant, and we'll see how a relatively simple servo can achieve that. Okay, so there can be other goals for servo systems as well, ones that involve more interesting uses of the control input. A lot of this technology was first worked out in the 1940s during the unhappy period of the Second World War, and things were like, okay, can I figure out a way to aim an anti-aircraft gun to hit a plane more reliably than a human operator? Okay, so sometimes you actually want to aim something, right? That doesn't seem to, I don't know an exact analog that's very interesting in our business, so I won't stress that anymore here. But holding the plant near a chosen operating point or modifying dynamics, both of those are really important for us. So I'll emphasize those kinds of applications. All right. Here is another slightly modified version of the same basic diagram, and it's been modified by labeling those blocks with capital letters that are supposed to represent the frequency response of each of these systems, considered as a linear input-output system in the frequency domain. Now, sometimes there are some situations where you can only make sense of the behavior of a system you want to control by working in the time domain. I know of such situations, and God save you if you're in one of those situations. It's hard. The easy situations to understand, the much easier ones, are ones where you can think entirely in the frequency domain. So I'm going to have us focus, except for one other parenthetical remark later, on situations where all of our physics analysis and understanding will be done in the frequency domain. So we'll think of the plant that has a ratio of its output to its input represented by a function of frequency capital P. The sensor gives an electrical, let's call it output to a mechanical input with a ratio of output to input represented by a function of frequency capital S. The filter is a dimensionless electrical input, electrical output box with a ratio of electrical output to electrical input represented by the function capital F. And the actuator is an object that gives, call it a mechanical output to an electrical input ratio represented by the function of frequency capital A. Now I wrote the Laplace frequency variable S. Don't hold me to that. I'm about to switch to plain old frequency with the letter F, and for our purposes today, that'll be fine. Now, so keep this in mind that if we go around the loop, let's say we start here, that we've got an output-input relationship P, another one S, another one F, another one A. Here is the most important mathematical object in the discussion of any feedback system. It's the mathematical object typically, and for me today, represented by the letter capital G, and it's a function of frequency, and it's equal to the product of the function P for the plant, the function S for the sensor, the function F for the filter, and the function A for the actuator. That's beautiful, even though you don't even know why I'm interested in it, but it's beautiful. Why am I asserting it's beautiful? What does this represent? Let's go back to that other diagram for a moment. If I have an input, say here, I'm really interested in what my control system does to that input. How it produces something here just where the actuator is about to feed back to the plant. As long as I'm doing my physics in the frequency domain, I can figure out what is the action of this whole thing, this whole system, by first figuring out what the signal is here by multiplying that input signal by this frequency response function. Then I've got another signal here, that's the input to this. In the frequency domain, its output, so long as this is all linear, is just the product of that times this. This signal is that input times this. So to go from this input to here is input times PS. To figure out what the filter says is the input times PSF. To figure out what the actuator would do is input times PSFS. That's what we've got. The product of all of the frequency responses of all the elements all around the loop. Now, if they're linear, no. Okay. If they're linear, no. But imagine, God forbid, that we didn't know about the frequency domain. And we were trying to solve this problem in the time domain in order to do the same thing instead of just multiplying 4 functions of frequency that I can probably do on graph paper. I would have to carry out a convolution integral on the input through the impulse response of this system to get another time domain function and do a second and a third and a fourth convolution integral, and I still wouldn't know what to do with it. But as long as I'm in the frequency domain and satisfying the requirements of the frequency domain that everything is linear, then the entire action of all those cascaded components around the loop is simply given by the product. And that product contains everything we need to know about the behavior of the servo. So we give it a special name, the loop transfer function. Or I often hear people call it the loop gain or the open loop gain. And in the learned literature, people try to tell you not to do that for various reasons. I may switch back and forth. But when I'm remembering to be proper, I'll call it the loop transfer function, the product of all of the frequency responses of all the components around the loop. So I want to help you understand how that turns out to be as important as I'm claiming that it is. And in order to motivate the claims I want to make, I'm going to state a theorem, which is the most important theorem that governs control systems. And This theorem says that let's let the frequency response h of f be any frequency response or transfer function between any 2 points in the system. And if I write it with no subscript, just call it h of f, I'm talking about the output to input ratio between my chosen output and input, wherever I choose them, with the loop not closed. Just all my components set up but not actually functioning. Yes? Thank you for reminding me to explain that. This is fabulous. Okay? All right. If I'm going to sensibly say that the output of the actuator does things to counteract disturbance inputs, this needs the same units as this and as this. On the other hand, I'm changing units at various places, but by the time I get back to here, I have to have been able to take an input in those units, transform it, and come back in those units. So the product of everything around the loop is dimensionless. Individual things have interesting dimensions. The only thing that doesn't, generally, is the filter. Maybe the plant has boring dimensions, mechanical noise in to mechanical noise out, but it doesn't have to. But irrespective of any particular example, a loop transfer function, by virtue of the logic of the diagram, is always a dimensionless function of frequency. Okay? Thank you. I meant to say that, and it's a really important thing, because I'm about to talk about values of G and how different values of G do things. And in particular, if you would look down to the bottom of the slide, you see I'm adding the number 1 to the function G, and that only makes sense if G is dimensionless. Okay, it's very important. So I could pick my transfer function H that I'm interested in to say just be the frequency response of the plant itself. Often that's the thing you're most interested in, but just in case you're not, just in case you're interested, say, in the transfer function together of the plant and the sensor, you can pick that instead. Doesn't matter, just pick any 2 spots, one in input, and this could be the output, or this could be the output, and in one case H is just P, in the other case H is P times S. So now the other symbol I want to define is H sub CL for H sub closed loop to be a transfer function between the same 2 points, the ratio of output to input in the frequency domain between the same output and the same input. However, H sub CL of F is what you get when the loop is closed. And let me just, I'm taking for granted that you understand something that you might not. Every servo needs a switch, because there's a lot of times when you don't want it to be operating. So either imagine that this wire can be pulled and disconnected, or maybe this one or this one, it kind of doesn't matter. Just imagine that there's a switch where you can literally undo a part of the connectivity of this diagram. Okay? In case that wasn't obvious, and there's no reason it should have been. Okay, so now here's the theorem. If I have my original open loop, uncontrolled frequency response or transfer function between particular chosen output and input, the closed loop version of precisely that same frequency response function is the original one divided by 1 plus the loop gain, or the loop transfer function. It's really simple to write. There's a lot of richness buried in that very simple to state theorem. But thanks for reminding me that this is the way to see how that units make sense and that they're not ridiculous. All right, now let's try to see. I think I now want to derive this expression. Okay, so here is yet another version of that same diagram. The only other thing that I've done is added a few labels to some well-chosen signals. So the input to the plant I'm going to write with a lowercase I for input, and that input is equal to the sum of the disturbance input added with, in the closed loop case, the actuator input. I'll call the output of the plant P, and I don't think in this derivation I need names for any other signals, so hopefully I remembered correctly. So let's see if we can make sense out of this, out of the logic of feedback in a way that will let us understand that theorem. So the first thing I want us to see from the logic of the summing junction is that the input to the plant I is equal to the sum of the disturbance input and the actuator's input to the plant. Okay, that's what that summing junction means. Now, let's think about what the actuation signal is itself. The actuation signal is the transfer function A of frequency times this signal. This signal in turn is equal to F times this signal. This signal in turn is S times P, and P in turn is I times capital P. So A is equal, I failed to make something else really clear. This minus sign is conceptually really important. Some place or other, I either want to say I've explicitly put in a minus sign, or I'll have to have a minus sign show up explicitly somewhere else. So I'm going to imagine that at the very last stage of my filter, I've got an inverting amplifier. Okay? So I'm going to explicitly put in that minus sign as well. So A is equal to minus I P S F A, writing it in the forwards order. Okay. A is equal to A times minus 1 times F times S times P times I. Okay, I don't, for this purpose, I'm not interested in the control input, right? There's no label here. We could always do a new derivation with that there as well. But let's just have one input. Okay, let's figure out the response to one input. Okay, so let's make this go away. Anyone want to challenge that line of the derivation or have a question about it? Okay. There is a direction of signal flow, and that's a crucial aspect of what's assumed here. That I can tell the difference between an input and an output depends only on the input of that box. In situations such as the mechanical connections between stages in a vibration isolation system, we'd better not break them apart. Okay? So the direction of signal flow, think for example, so mechanical things are maybe kind of weird and you worry, but think about how we design electronic circuits. Okay? Except when the thing is about to catch fire, the output is proportional to the input and the output doesn't disturb the input. Okay? But that is a good point. Is there a simplification that I can make here? Thank you. Right? So A is equal to minus IG. Now let's plug in for A in that first line. And now I have I equals D minus IG. or I plus IG equals D, or I times 1 plus G equals D, or I equals D over 1 plus G. And now, what if the transfer function that I'm most interested in, the closed loop transfer function, is in fact P, and I'm interested in the ratio of its output to the only input that comes from the world, namely D. So P, which is equal to the ratio of P over D, I would just have P closed loop equals capital P over, I'm sorry, lowercase p over D, and that's equal to capital P over 1 plus G. Now, there was nothing that I did that required me to pick P. I could have picked any other input-output pair, could have picked P times S or whatever. The logic of the derivation goes just the same. So, because the action of this feedback has been to make the net input to the plant be the modification of the disturbance input divided by 1 plus G, then the output of the plant is also modified by dividing by the same denominator. I'm not sure I'm seeing every head nods. Did I go too fast in that last step? Okay, let's do it more slowly then. Thank you. Right, right. So, well, D is autonomous. D comes from the world. Okay? What we're interested in is figuring out what the input to the plant is given that the autonomous existence of the disturbance input. Okay, so I'm not trying to learn anything about D here. I'm trying to learn about what I is to the plant given D and given the action of the loop. So this is the crucial intermediate result, that the net input to the plant when we combine the actuation input with the disturbance input at the summing junction is to take what would have been the input if the loop were open. The input to the plant I would be equal to D. But with the loop closed, with us combining A and D, the combination of A plus D making I gives us an I that's equal to what would have been the otherwise autonomous input to the disturbance input to the plant D. We're correcting it, dividing it by 1 plus G. And in the simplest case where G is large, which is the thing we often want, we have made the disturbance in the net input to the plant much smaller than the original disturbance input. That's the best example. Yes? You want me to write AFSP? AFSP instead? I'll do it. I'm sorry? Okay. I is a is a function of frequency representing the Fourier transform of a time series. Okay? And each of those letters, capital letters, represents an output to input ratio that is some function of frequency with, in general, a constant, overall constant that may have dimensions or may not. So they're not matrices. No, no, no. They are scalar functions of frequency. Okay, and I'm allowed to multiply them in any order. That does not matter. I get the same answer when I'm multiplying scalar functions of frequency together. Yes, now. Because, good. Excuse me for doing this. All right. I want everything in my control system to be in a black box. Okay? I want to say, you know, if I really want to, I can stick my finger in and feel that actuator pushing, but I'm not interested in that. Okay? I'm interested in the function of some system. I know it's being shaken by the world, and it has an output that I care about. So I am literally only interested in the behavior of the output in response to the input. If D goes away, if D becomes precisely 0, so will P, and I don't need anything. Okay? So I really care about the ratio of P to D, and I'm using the trick that inside my box, I've artfully constructed an A that acts as a second input onto my plant, so that the net output of the plant will be, in this case, smaller. That's part of the functioning of it all. But my interest is to say, once upon a time I had a plant, it was being disturbed, that disturbance caused its output to be bad. Now I'm going to wrap that plant with something amazingly, magically well designed, so that when that same disturbance input comes along again, I get a different, better, usually smaller output of my plant in response to that disturbance input. So the ratio of P to D is what I care about, and that ratio of P to D is modified deliberately by all this action. But I don't need to keep separate track of A except by virtue of how A has been constructed to be magically almost perfect at canceling. And to make this a little more obvious, let's imagine a situation where the loop transfer function, or the loop transfer function G, is huge. Okay? Factor of 1,000. I often want that. And we'll see later the circumstances under which one can or can't achieve that always. All right, but that's my goal. I really want the plant to respond less. So P over G is 1,000. That says the closed loop response of the plant to the disturbance input is only 1/1000th what it was before I did my good control engineering. That's my goal. And this derivation shows me, oh, okay, here's the hand waving. When G is 1,000, that means that the product of all these frequency responses going around the loop makes A such a good match to D that the mismatch is only at the part in 1,000 level. And so when I add this, remembering that there was a minus sign to make it so that A is there to counteract D, G being 1,000 means I've just got a factor of a part in 1,000 mismatch between my control, between that actuating signal and the disturbance input. It's there to be almost a perfect match, and I do it by constantly measuring. Now, is it the algebra that's troubling, or the fact that this seems like too good to be true? Right. It's the ratio of the output of the plant to the input of the plant when the control loop is closed. Alex, you have a question?
Again, the minus sign, because that makes a big difference.
Yeah.
If you have 1 minus g. So again,
Mhm.
how did we get this minus sign?
All right. It's a deliberate choice, okay? What I need to do is end up with a situation where D and A look like they are almost, that A looks almost like a perfect copy of D, but I want the version of that perfect copy so that when I put them together at a summing junction, they cancel. So now, look, this is all notional. If you actually go out in the world, all right, let's say the plant I want to control is some mass on a spring and it's bouncing up and down. So I want to apply a force, an extra control force to that mass and have it not bounce up and down so much. Now, I can measure how much it bounces with the sensor and I can manipulate it, whatever. At the end of the day, I want to make sure, if this is going to do what I want, that when the outside force pulls down, my control force pushes up. So I can either say I put an inverting amplifier here, or I can flip which wire goes to the one end of the coil that makes the force. Okay, adjusting signs you do. Okay, but the goal is, you know, combine the outside world's influence and my controlled influence in as perfect a way as I can. Okay. Anyone want to raise a hand, or shall we mull and take it maybe that I did it right and we can talk about it more at lunch or dinner? All right. Did I at least write with chalk something that looked like a proof of the theorem? Okay. Yes. The response time. Very good. Let's hold the response time question. Um, and how soon are we going to get to an all right, let me give you a short version of the answer, and I will give you a more formal answer before we break for lunch. The short version of the answer is that in most situations, most electronics respond so quickly that the notion of a delay time is not the most important breakdown of this model. However, there's something that is very important that's almost like a delay time, and that's the following. In order for this cancellation to be really good, my ideal would be to have G be huge and have G be huge up to arbitrarily high frequencies. That's my ideal. Now, a time delay would be one way that makes it impossible to have G stay huge up to arbitrarily high frequencies. But what's more often the case is either that one or more of these components introduces a phase shift so that for whatever reason that's beyond my control, I can't make this be really faithful because at high enough frequencies I can't track things. Or what tends to be the case is that I must deliberately insert a phase shift because one or more of my components can't be considered at high enough frequencies to have the same faithful relationship between input and output. And here's the classic example that I understand. So let's say I'm going to push or pull on this object I want to bounce less, but one of the parts of that pusher is a mechanical strut of some length. And I actually push on one end of it, but the effect comes from motion of the other. There's a frequency that, unfortunately for real materials, is not that high, at which there's a resonance in that strut, and then I go from there being an in-phase relationship between motion of one end and the other to an out-of-phase motion. That's the commonest breakdown of what you want to do. And when I get back to the formal answer to your question, I will show you that what you need to do in order not to build yourself an unstable servo is to deliberately introduce gain declines, which also bring in phase shifts, so that you're not trying to do anything interesting at the frequency at which that resonance happens. So let's keep alert for phase shifts and resonances as the reason that you can't do what you obviously want to do. I mean, look, I don't even need to be a control engineer to know that I want G to be big, usually, and that I want it to be big irrespective of anything else about the signal. So it should be big at all frequencies. But I need control engineers because it never works that way, for the reason that's like your question, but just subtilized a little bit. So we'll make it a little more subtle in a moment. Okay, these are all good questions. I will keep taking questions, but since no one is raising their hand at this moment, I'll show the next slide, but you're welcome to, I would rather, yes, go ahead. So you mean what if, I think that's a great question, what if D is the gravitational wave? Okay, and what if, say, the sensor output is our record? You are correct that the action of feedback is to reduce the amplitude of the recorded signal so long as we're in the regime that we're trying to achieve, namely where G is big. However, I may not care about that. Here's why. At the end of the day, I want to know what would have been the response of the plant to the gravitational wave input. If I happen to reduce it for technical reasons because I need to make sure that I always stay within the linear operating range, I've changed the calibration of the signal that I would have recorded to disk down here to something that's smaller. But if I've done that in a linear way, and if I've done that with components well chosen so that I don't artificially reduce this signal below the level of the input noise of the amplifier I'm using at the input of my A to D, as long as I'm not in those situations, I don't care. I just need to keep track of this as part of the calibration. Okay. Yes. If your electronics is bad enough, it can introduce additional noise. It is one of the challenges of control engineering to ensure that you never use an amplifier that has too much noise referred to input so that this comes to pass. Okay. Yes. You mean if I'm using a magnetic actuator and then there's a new path for a new disturbance input to come in? Yeah, that can happen. Don't do it. No, really. And the worry is real, and my smart aleck reply is real. In initial LIGO, the actuators on the mirrors that we pushed to ensure that the mirrors separation stayed close enough to resonance so that we had a linear response, those actuators were little magnets glued on the backs of the mirrors, and there was a coil through which a control current was pushed. And yes, there's magnetic coupling. And yes, we've removed those magnets because, you know, that was too bad. It was for our new specs. And we've got magnets one stage up. And do they still cause something of a problem? Yes. Okay. So it's an excellent question. Something that I want to leave you with is, at the end of the day, even though this diagram is challenging to understand, at the end of the day, it's not a challenge. I've either given you a correct derivation or not once we figure out the answers to all questions. However, questions like, do I have sufficient bandwidth to do what I want to do? Or have I inadvertently brought in new coupling paths for new disturbances? These are all real life problems. Okay? So it's not magic in the end. It does quasi-magical things, but most control engineers most of the time are tearing their hair out because their employer gave them a specification. You've got to achieve this. And everything you try either brings in some other noise coupling or doesn't have sufficient bandwidth to give you a big enough G at the frequencies you want or something. Okay? So you have to always check that the amplifiers are quiet enough and that there's no new noise coupling paths and that I've got sufficient bandwidth. Okay, this is all true. All right. I'm going to talk about this slide unless someone raises a hand. Okay, so this being the key theorem, I obviously think that there's something interpretable about it, and there's lots that is interpretable about it. First of all, for the very common situation where our goal with our servo is to hold something close to an operating point, then we can see what is the key desideratum of that denominator, excuse me, 1 plus g. It is that 1 plus g be as big as possible. We'll see other situations where that's maybe not our goal in a moment, but in any case, 1 plus g in the denominator is how we modify the behavior in the absence of control. And there's kind of a few interesting limits. 1 plus g huge, g much less than 1, so that 1 plus g is just 1. And then the really tricky case where 1 plus g is of order 1. And remember, g is a complex function of frequency. So g could be minus 1 and then something horrible happens, or it could be I, or it could be whatever. Okay? So we got to keep track of phases as well. All right. So this is the key theorem. All of the benefits of feedback are encoded in the loop transfer function because this is the key theorem. Now, let's talk about an example, and this particular example has dynamics. I think that's simple enough for us to do graphically, and it's not a case where what we want is G huge, but we want some other benefit of feedback from this situation. So here is the problem. We've got this high Q pendulum. We don't want it to ring for hours after a disturbance because just locking the interferometer is a disturbance, and we want to be taking data. So we want to somehow modify the dynamics of this pendulum. So here's our plant, high Q pendulum. Here is a sensor drawn as if it's a human eye, some photodetector looking at some edge that gives a voltage output that's linearly proportional to the center of mass position of the pendulum. An actuator, which I've drawn as a boxing glove, but it's any kind of thing that you use to apply a force. And in the place of the filter, I've drawn in something that to me at least suggests a particular filter choice, but let me pretend that it might not be obvious to you. Maybe it really isn't obvious, and we'll come to that in a moment. So that's the basic layout, and we have to see whether we can figure out how this servo ought to work and whether we can make it do what we want. So let's remember, first of all, what is the Bode plot? Remember what that is? Magnitude of, I think I'll call it P of F, and phase of P of F as a function of log frequency, and this is actually log of the magnitude of P of F. And remember, what we're dealing with is a simple harmonic oscillator, and the question is, if I, in an open loop way first, so completely disconnect what's at bottom, inject sinusoidal signals of arbitrary frequency to the input of this actuator, cause my pendulum to move and sense how it moves. That's a plant transfer function. And we talked about this before, and you saw it with my shoe. At low frequencies, the frequency response of a force applied to a suspended shoe is forward force, forward response, and at low enough frequencies, frequencies below the resonance, it's one number. At high frequencies, the shoe's inertia resists, oops, and the response falls like 1 over frequency squared. And then there's a resonance, which in this case is 2 high Q for us. And what's the phase relationship? In phase at low frequencies. So phase between output and input is 0. Out of phase at high frequencies. And that's what happens in the middle. Right on resonance, which is easier to see if it's low Q than high Q. There's a 90-degree phase lag between the response. Okay. So this is the key undesignable, built into the plant part of the loop transfer function. Now, we would like a loop transfer function whose job that will have large values of 1 plus g near the resonance, so that 1 plus g can be in the denominator, and so that the closed loop version of this won't go to such ridiculously high amplitudes. We don't particularly care to have large values of 1 plus g far from the resonant frequency. In fact, we don't even care to have particularly large values of 1 plus g on the wings. We're happy to end up with a well-behaved few cycles to damp away. Okay? So, I'm going to propose the following. I'm going to propose, just for purposes of intuition, that what I would like to do is use this system to apply a damping force that's only strong right at the resonant frequency. And damping is a velocity-dependent force, right? So I'm going to make a filter that takes the derivative of its input. If I were doing this with analog electronics, I would make a simple filter that approximates a derivative, but for purposes of this example, we could make a derivative, have some adjustable gain and some appropriate sign so that I know that the damping force is coming in with the right sign to suck energy out of the oscillation and not pump more energy in. A derivative, remember the Ansatz solution to our equations of motion depended on the property that the derivative of e to the I omega t is I omega e to the I omega t. That means a derivative operator takes any transfer function and multiplies it by I omega. That is to say, tilts this upward by 1 power of frequency in this part of the diagram and shifts this to by 90 degrees there. So if I build my filter to be a derivative with an adjustable gain and an appropriate sign, then the Bode plot of G looks like, instead of a constant function of frequency, 1 power of frequency, gigantic bump, 1 power of frequency declining instead of 2. This goes from plus 90 degrees, sorry, I use degrees when I talk servos, pi by 2 if you prefer, to minus pi by 2. And that is the functional form of the loop transfer function that I've designed. Now, does it do what I want or not? Now we have to ask that question. But I'm proposing this as a functional form that might do what we want. What if I set my overall gain by my adjustable knob in my electronics of my differentiator so that this is the level that corresponds to G equals 1? Okay, I'm free to do that. I assert that that's an interesting choice. That means here G is much 1 plus G is much larger than 1. Here 1 plus G is just 1. And as a result, my closed loop version of this transfer function is only going to be modified near the resonance. Near the resonance, its magnitude is going to be pulled down by 1 plus G. So I'm going to take this and I'm not going to change it at all at frequencies far from the resonance, but I'm going to turn this sharp peak into a low peak, and it otherwise behaves just the same. So I've been able, by this example, to show that I can build some electromechanical feedback that allows me to modify the dynamics of my plant in a way that was desirable. Yes? I'm sorry? Yeah? Or that we don't need to bother. Okay. What can I say? This trick is used often. It's definitely used for pendulum modes and other rigid body modes. It's also used to damp some high frequency modes, which are the truly troublesome ones because they come into the dynamics of the interferometer in ways that are tricky. But here is the problem, and this is related to your question as well. A generic feature of the world is that once you're in the frequency regime where there's one mechanical resonance, there's another one and another one and another one and another one lurking. And we are seldom in situations, unfortunately, where it's just a harmonic series. Sometimes we are, like violin modes make a really good approximation to a harmonic series. Modes in things, three-dimensional things like mirrors, suddenly there's a forest. So you can build things that work this way for some finite number of modes, but you can't keep using the trick and make it as if there are no resonances that ever exist in your apparatus. Okay, so we've changed dynamics of the plant, and mindful of the time, I am just going to wave my hands about my next example. You don't need that. There's the graph of what we just showed. This borders on the miraculous, but I don't know that we have time to analyze it in detail. So here is a vibration isolation system. The passive version of this I will take to be my plant. Here is something sitting on the ground. Here's a spring connection to a mass that's free to vibrate, another spring connection to another mass that's free to vibrate. This should give 1 over f squared. That should give another 1 over f squared. But maybe I'm not happy with that. Maybe I would like that's the plant transfer function. Maybe I'd like to help it out. You can imagine helping it out in the following way. You can imagine building a sensor that looks at the difference between the position of this mass and this mass, that is to say, at how much the spring is compressed or stretched, and then apply a control force to this mass. It's not the only thing you can do, but you can do that, and you can ask what that does. Here's some hand-waving insight to build some intuition. When does this spring depart from its rest-loaded length? It departs from its ordinary loaded length when this mass is either accelerating upwards or downwards. So, the measure of the length of this spring is a measure that this mass is not sitting perfectly still. Even though it is isolated, it's still being shaken somewhat. You can, if you build this loop, just like what I showed you before, the measurement of the position of that pendulum mass is something you can use to either determine the position or multiply it by a derivative operator to get a frequency. Looking at how much that spring is stretched or compressed is telling you about the acceleration of this mass. So, putting my sensor there multiplies this plant transfer function into something that comes out of the sensor, where this goes like 1 power of frequency squared and this goes down. So I've tipped this whole thing by f squared, like an acceleration. Now, maybe I want this place to be g equals 1. It's a free choice. Some are better than others, but there's a knob. I can choose it. If that's the case, here's the region where g is much greater than 1. Here are the two regions where g is much less than 1. And here are two danger regions. If you do things carefully, the closed loop response adds some artificial vibration isolation at a resonant frequency that is lower than any mechanical resonance in the plant, and whose frequency depends on how high up I turn my knob. It ends up giving lower transmission of noise in this mid region. It builds another resonance here. Now, if we just did what I just showed you, in fact, this becomes the worst behaved servo in the world, and these two artificial resonances either have incredibly high Q, or worse, and here's where I'm going to say this word for the first time, the servo goes unstable. Now, here is where the fact that we have a filter saves us. Because I don't have to precisely use the output of that sensor. I can modify it at some frequencies, and given the closeness of lunch, I can't describe to you what that filter is, but I can make it so that instead, I can show you this. Okay. I should have shown you the phase part of the frequency response. Here's why it's twitchy. There are two 180-degree phase shifts with two resonances. That means that if I choose the appropriate sign for negative feedback in this mid-frequency range, which is what I want to do, I want to make my actuation function cancel as close as I can my disturbance input. That means off to the low frequency end and off to the high frequency end, I've got the wrong sign. And 1 plus g is almost 0. 1 plus g being almost 0 is what creates these artificial resonances. So what I have to do is modify, is filter this signal so that the net effect is to pull the phase away from -1, at least at frequencies near the place where the magnitude of g is about 1, because if it's g is about equal to -1 and I have 1 plus g in the denominator, that's what's terrible. But if I can make g be, have some substantial phase away from -1, I can make this be well behaved. That's the generic reason for why I need those filters. Now, does the magic work so well that I should just crank G up as high as I can and build myself more artificial isolation? That's my desire. My customer wants that. However, here now is where your question comes in. This transfer function never smoothly goes like 1 over f to the 4th forever. It starts having all sorts of resonances. Those resonances show up here, and a substantial subset of those resonances add extra 180-degree phase shifts between input and output. And if I tried to make my unity gain be all the way down here, I would be in a situation where instead of giving me extra isolation and some weird, slightly twitchy resonances, I would actually send the system into full instability and shake it apart. And I've built some things like this and turned it up too high and almost destroyed them, okay? Instability in mechanical servos is a frightening thing, okay? So there's always a limit to how high you can turn up G, and it's usually because you've lost control of the phase at high enough frequencies, and you have to ensure that you never put places like that in a situation where the denominator 1 plus G can become, the denominator 1 plus G can be too small. Nevertheless, this can be made to work. Here's a slide I showed you before that's almost indecipherable, that represents the fact that 2 stages of a system like this are built into advanced LIGO and are working routinely and well. Here is something I would have taken more time, but this was more important to talk this other stuff more slowly, that shows how it's actually built. But the key thing is that there are platforms and there are seismometers, which are suspended masses on springs, so they play the role of the top platform. Okay. Now, this would be kind of complicated to do anyway, so I will instead tell you war stories of how it is that you lock a resonant Fabry-Perot cavity using the Pound-Drever-Hall technique. Here I remembered to put in the actuator as well as the RF sensor system. I'm not going to explain that RF sensor system, but I am going to point out that here is the functional dependence of the output of that RF sensing system, the output as a function of distance from resonance. And note the crucial thing, that it's only a linear connection between output and the thing you want to measure, distance from resonance, over a very small range. And outside that very small range, it gives you nonsense. You cannot control a system with a nonsense error signal. You need an error signal that is a linear relationship to what the thing you want to measure and control. And we need to do this over and over and over. We need to do it for many degrees of freedom. There are 4 key degrees of freedom and a gazillion auxiliary degrees of freedom, that's a technical term, in the length control and in the angle control. Angle tends to be less twitchy. It doesn't tend to have this problem as the Fabry-Perot degrees of freedom do. When you're trying to lock cascaded Fabry-Perot cavities, if you're not smart, sometimes you'll lock one cavity, sometimes you'll lock an arm, sometimes the other arm. To get everything resonating is difficult. Here is the horrible thing. It's okay to confess this, Alan, that when we asked for the several $100 million to build initial LIGO, we did not know at all how to lock it, how to simultaneously get all of the cavities together to lock. And when we finished installing all the components at the 4-kilometer sites, we still did not know. So what did we do? We gave it to a grad student. Said, okay, your project is to save LIGO. A really good graduate student, Matt Evans, right? And he did it. But I'll now tell you the story. All right. It was the 20th of October, 2000. So we had blown through 230 some million dollars. And only on that day did we know that we could make the thing even begin to work. I didn't grab the slide from the report given by Stan Whitcomb later that day where he showed the first noise curve and he said, we have to reduce the noise between 5 and 6 orders of magnitude. But now we're working, all right? But boldness or humility, which was this? Okay, so here is one version of the party in the Hanford control room that day. Here is Ray Weiss, Robert Schofield, and Bill Kells. The crucial thing from the physics point of view is this set of 4 video camera images. That's the light resonating in the Y arm. That's the light resonating in the X arm. The cameras didn't have the same lenses, so they don't look the same. This is the light resonating in the so-called recycling cavity between the power recycling mirror and the beam splitter. This is the light that was bouncing off the back side, the input side of the recycling mirror. This is the only place you see light before everything is locked. And for weeks, for months, Matt would be in the control room. You'd see one of those other 3 images blink, 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 but not all together. Here's the real party. There is the hero, Matt Nergis. There's Stan Whitcomb, who's the head of LIGO commissioning, among many other roles he's played in LIGO over the years. Here's Dave Ottaway, Mike Landry, who's now the head of the Hanford Observatory, Luca Mattone. Okay, and all right. So already more work to do. That's why Matt and Nergis are not paying attention to the camera, because they're trying to figure out how to make it better, because look how well it worked that first day. It stayed locked for 2 minutes. And during that lock, the power resonating in the arms, changed by order unity. It's horrible, horrible. And the noise was 1,000,000 times too big. All right. It's hard to keep things stable. It's very hard to simultaneously have servos be stable and have G be as big as your customer wanted it to be. That's what's hard. And every time you think of a way to change the filter to make G bigger in some frequency range, the Kramers-Kronig relation bites you and affects the phase in such a way that it takes away a huge portion of the advantage you thought you built in. If you are not a master of complex analysis, you can't design filters properly to do this job. I want to, since it's lunchtime, just close with a few personal remarks. I've been struck by feeling the spirit of Cécile de Witt-Moret here. She made a too small an appearance in my first lecture. She and her husband, Bryce DeWitt, were the organizers and conveners of the Chapel Hill Conference in 1957, which played a fabulous role in our field by resolving the worries about the reality of gravitational waves and launching the program to find them. If she had not been doing that job in 1956, leading up to that 1957 meeting, none of what brought us here together would have happened. We've come together in the house that Cécile de Witt-Moret built. She founded this fabulous school. Here she is around the time she hosted the Chapel Hill Conference. She just passed away a little over a year ago. Here she is late in her life. Her spirit is everywhere here. Here she is taking a break, I guess, from the Les Ouches conference with her friend, hiking near with her husband, Bryce. Have you ever seen more life in a smile? I haven't. And thinking of her makes me realize, how much gratitude we need to feel and occasionally to articulate. All right, we're having a fabulous time here. The place is beautiful, the food is great, the program is well organized, you know, you students are really active and engaged. It's wonderful. Partly that's due to us, let's say, but it depends on so many more people than us. We should not take for granted what Pierre-François and Marianne and Nelson and Bruce have done to bring us together, but the list of people we would need to thank goes on and on and on. We need to thank Cecile the physicist as well as Cecile the organizer. We need to thank the heroes of that 1957 conference, Pirani and Weber, Weiss, who digested it all and got us pointing in the right direction. We need to thank our families, our friends, the taxpayers, everyone. There's so many people who sacrifice so that we can have a great experience here. To say nothing of nature, who provided us with this wonderful signal that we found. So let's, I'm feeling tremendous gratitude. I'm sure that all of you all are as well. And since after dinner tonight I won't have a chance to see you all at least together, I'd like to offer you a wish that as our future world lines diverge, each of us has to pick our own path through life. Make sure that you pick one that is a path that you can love. Thank you all.